All right, welcome to today's notes. I wanted to start with a warm-up. It's not actually in the notes, but I wanted to explain why we're jumping from average rate of change to the lessons that we are jumping on. So I've got this function here. I want you to calculate the average rate of change on the interval a to a plus h. I encourage you to pause the video and try it on your own. As a reminder, average rate of change is f of b minus f of a over b minus a. So I did the function of b minus the function at a all over b minus a. And we want to simplify this expression. The denominator simplifies pretty nicely because a and negative a cancel each other out. But we're left with this numerator and the question of whether or not we can simplify this numerator. And so the way we're going to go about simplifying the numerator is finding common denominators. And if I take my first fraction and multiply top and bottom by a, I'll have a common denominator. And then if I take my second fraction and multiply top and bottom by a plus h, what winds up happening is my two fractions have the same denominator, and therefore I'm able to combine them into a subtract a plus h over a times a plus h. And this is being divided by h. Okay. So let's clean this up, see if we can go any further with this. A subtract a cancels out, and we have subtract h on top. And then dividing by h is the same as multiplying by 1 over h. And we see h's cancel, and we wind up having the statement negative 1 over a squared plus ah. Now, admittedly, this is a more advanced, or I'd say mid-level average rate of change problem. We are flexing on our algebra skills. And eventually we're going to start to learn some shortcuts to move from this to our desired goal. Our desired goal has to do with what is our average rate of change on this interval as h gets smaller and smaller and smaller and approaches the value 0. And so, in theory, if I were to take this expression and say, let h be 0, what I'm doing is I'm saying, let's take the limit as h approaches 0 of this expression. And for now, it's kind of like just saying plug 0 in for h. And if I were to plug 0 in for h, I'd get the answer negative 1 over a squared. So, the focus of today's lesson and many more that follows is exploring what exactly is this mathematical piece, the limit, and what does it mean, and how we're going to use that to set the foundation for calculus. So, the answer to the warm-up is right here, and then the reason we did the warm-up is to introduce this as our segue into the meat of this unit, an exploration of limits. Okay, let's take a look at the notes. To understand what limits are, let's look at an example. We'll start with the function x plus 2. So we have f of x equals x plus 2. The limit of f at x equals 3 is the value f approaches. So we're looking for this concept of the word approaches as we get closer and closer to x equals 3. Graphically, this is the y value we approach when we look at the graph of f and get closer and closer to the point on the graph where x equals 3. Okay? It's going to be a little more subtle than that, as we'll see. But for example, if we start at 1, 3, this location right here, and we move on the graph until we get really close to x equals 3. So we're moving rightward until we get closer and closer to x equals 3. Our y value that we approach is the value 5. So what this is saying is the limit as x approaches 3 from the left-hand side of the function is equal to 5. I'll read that again. Limit as x approaches 3 from the left of f of x is 5. Now, some mathematicians prefer to use arrows right here because we're not setting it equal to 5, we're saying it's approaching 5, but either method works. I tend to use equals sign, but there might be discussion in calculus classes to which is better. Similarly, if we start at 5, 7, this point right here, and we move to the left until we get really close to x equals 3, so we're going leftward, 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 leftward until we get to this point where x equals 3, the y value again is 5. So what this is saying is the limit as x approaches 3 from the right, that's a plus sign, of f of x is also 5. So if I approach from the left-hand side, I get to the height of 5. If I approach from the right-hand side, I get to the height of 5. And so we can merge these two statements into the single statement, the limit of f of x at x equals 3 is 5. Or notationally, the limit as x approaches 3 of f of x is 5. This encapsulates both the left-hand limit and the right-hand limit. Since the left and right agree, and that value is 5, then the two-sided limit is 5. And several of our notes over the next few days is going to focus on finding the left-hand limit, the right-hand limit, and the two-sided limit. Now you might be saying to me, well, why don't we just evaluate the function at 3? For example, let's just stick 3 into this equation. 3 plus 2 is 5. Ta-da! There's our answer. Why did we have to go through this process? Well, the reason we went through this process is because sometimes it's not as simple as just plugging in the number. In this case, it was. F of 3 was the same thing as the limit, and that value was 5. But let's look at a different function. In this case, g of x. This is a more complicated equation, and if I were to evaluate this expression at x equals 3, if I were to evaluate g of 3, I would do 3 plus 2 times 3 minus 3 over 3 minus 3, and I would see that I'm dividing by 0, and that causes an error. There's an error inherent in dividing by 0, and so that's not allowed. However, I assure you that the limit does exist on this function, even though it is not defined at 3. And we're going to explore that on the next page. So let me drop in a few other extra words in here. I said it, but I think it's worth writing. This is called the left side limit, because we're approaching from the left. This is called the right side limit, because we're approaching from the right. And this is the two-sided limit. Two-sided limit, or just the limit. Okay. All right, let's see this equation on the graph on the next page. Visually, this graph looks exactly the same except for one small detail. At x equals 3, the function was undefined, and so the graph winds up having a hole at this point. A hole. Or sometimes you'll see me write it as this funny looking symbol here, and I'll explain that further on down the road, but it has to do with, I'll explain it now. We had the x minus 3 on top and the x minus 3 on bottom, and they canceled each other out, so there was a hole at 3. So, okay. But here, our left side approaches 5, and our right side approaches 5. So because the left side approached 5, and the right side approached 5, because both of them approach the same value, we're going to be able to say that the two-sided limit is in fact 5. Even though f of 3 is undefined, we can still talk about the limit, or sorry, g of 3. The function is g. So the limit of g at 3 is equal to 5, but the value of g at 3 is undefined. Let's call all of these g's, since the name of our function is g in this case. Okay. Take a breather and digest that.
All right. As we see, that's the beauty of limits. They don't depend on the actual value of the function at the limit. They describe how the function behaves when it gets close to the limit. So here's another curve. We don't have the equation this time. We see that it's coming up. There's a hole right here at 3. And they say, what is the limit as x approaches 3 from the left of the function h of x? Well, as we approach 3 from the left, we are getting closer and closer to a value of 2. Then it says, what is the limit as x approaches 3 from the right of h of x? Well, as we approach from the right-hand side, we are again getting closer and closer to a value of 2. So what we have here is a left-hand value of 2 and a right-hand value of 2. And because they agree, we can say the two-sided limit is also 2. Finally, they ask the question, what is the value of h of 3? And h of 3, we can see there is a hole there, so h of 3 does not exist. And therefore, h of x is not continuous. More specifically, it's not continuous because it has a hole. Okay. So the sequence of finding these 4 values is a way to determine if a function is continuous. If all 4 of these values are the same, then the function is continuous. But if there is any discrepancy, then the function is not continuous. And this leads to the definition of continuity that we will use in my classroom. The definition that I use is if the limit as x approaches a from the left of the function is the same as the limit as x approaches a from the right of the function, which is the same as the function at a, then f of x is continuous at x equals a. Left limit equals the right limit equals the function. And if these two equal each other, then the two-sided limit works. So we're looking for these 3 numbers, and if these 3 numbers are the same, then the function is continuous. Incidentally, finding left and right will give us the two-sided limit. So technically, you don't need to actually state that to see continuity, as long as you have these 3 numbers and they are the same. So that's not the case here. All right, let's look at the next page. The limit as we approach 6 from the left. Well, as we approach 6 from the left, we get closer and closer to a value of -3. As I approach 6 from the right-hand side, I am also getting closer and closer to a value of -3. Because my left-hand limit and my right-hand limit are the same value, I can say the two-sided limit is -3. However, if I evaluate the function at 6, I get an answer of -5. And because these numbers are not all the same value, we can say f of x is not continuous at x equals 6. Okay? Originally, we approached the idea of continuity as, do you have to lift your pen to draw it? And if we are drawing this curve, we would come down, and then we lift our pen, put a dot, jump back up, and then continue the curve. But now we have a more formal definition for continuity. Okay? And then finally, before closing out this video, we're just going to finish example 3. Translate the following sentence into math notation. the limit of x squared as x approaches 5. So we should be pretty fluid with moving between words and symbols. The limit of x squared, so the limit of x squared as x approaches 5. As x approaches 5. We don't have anything for what this evaluates to, but if we were to take the time to think about the graph x squared, which is a parabola, as we get out to the value of 5, what is that curve doing? Well, it's continuous through that point, so we know if we were to evaluate, then we would get whatever the y-coordinate is, which is 25. All right, we're going to continue the notes in the next video, but until then, be sure to mash that like button, comment, subscribe, hit the bell for notifications. Thank you.